7.3 Exponential and Logarithmic Problem Solving. Before we solve actual word problems, let's do some just general stuff. First, let's talk about the properties of equality. If I have the same bases to different exponents, then the exponents must be the same. Likewise with logarithms, if I have logarithm to the same base to two different things, then those different things must also be equal, okay? With some normal caveats of logarithms. Okay, let's use that to solve this equation. Now, I want to take advantage of the first one here where the bases are the same. And I know that 16 is a power of 4. It's 4 squared. So I'm going to write 16 as 4 squared to the quantity 2x plus 3. And then 1/4 I'm going to write as 4 to the negative 1. Okay, to the 7x minus 1. And then I'm going to take advantage of the power rule for our exponents that I can say multiply the two. So this becomes 4 to the 4x plus 6. This one becomes 4 to the negative 7x plus 1. And then, since the bases are the same, I can equate the exponents and then proceed to solve for x. Take the 7x over to the left, take the negative 6 over to the right, and then divide by 11. And there's my answer. Second one, let's take this one now. 25 and 125 I know are both powers of 5. So I'm going to write 25 first as 5 squared, and 125 is 5 to the third. I'm going to say 5 to the second is the same as 5 to the negative 2. And then I'm going to multiply these exponents to get 5 to the 6m minus 2 equals 5 to the third. And then set 6m minus 2 equal to 3. Take the 2 over to get 5 and divide by 6 to get m is equal to 5/6. Okay, now I want to take the logarithm of each side, but before I do that, I want to isolate the 10 to the 6x. And I'm going to do that by dividing out the 11. So divide each side by 11, and I get 10 to the 6x is equal to 5. Now I want to take the log of both sides, because I know these are kind of inverse operations. The log of 10 to the 6x is just 6x. Log to the 5 is just a number, all right, which we will find out later, I guess. Log of 10 is equal to 1. So now this becomes 6x is equal to the log of 5. X is equal to the log of 5. And then once I enter all this stuff into my calculator, I get 0.116. And that's my answer. All right, what about this one? Before I take this to 10, before I take the log of this, I want to isolate this 14 to the 9n plus 8. I'm going to treat this kind of like a variable, like this is 9x plus 7 is equal to 97. First, I want to isolate this. And I do that by doing the same thing as if this were just an x. First, I'm going to subtract out the 7. And then I'm going to divide out the 9. And I get this. Okay? Now let's take the log of this. Okay, now, I know the log of 10 is equal to 1. Okay, and then I'm going to pull this out of the logarithm, so it becomes 9n plus 8 quantity times the log of 14 is equal to 1. Okay. All right, my calculator said that 1 over the log of 14 is this. I'm going to then subtract 8 to get this, and then divide out 9, and there's my final answer. All right, let's see here. Exponentiate both sides. All right, and I'm going to take e to this eventually. But first of all, I want to isolate that by adding the 5. So I'm going to add the 5 to get natural log of x minus 6 is equal to 9. Now I'm going to e both sides. All right. That just becomes x minus 6. And e to the 9th, according to my calculator, was 8,103, which I will then add 6 to get my final answer, 8,109. All right, what about this one here? Okay, first of all, I'm going to isolate the log to the base 2 of b by subtracting 7 from both sides, and I get this. And then, if you remember the definition of a logarithm, it becomes 2 to the negative 10 power is equal to b. Okay, that's by definition a logarithm. All right, and then I can write this 2 to the negative 10 is 1 over 2 to the 10th, or 1/2 to the 10th power, which we can also write as this. And then whatever 2 to the 10th power is, you could have that down there as well. All right, whatever that becomes. Okay, next, let's see, what about this one here? So first of all, I'm going to subtract, I'm going to add 5 to both sides, treating the log to the base 3 of n minus 10. I'm going to treat that as its own separate variable, which I want to isolate first by, first of all, adding 5 to both sides, and then dividing out to -7, and I get this. Okay. All right, now, since this is log to the base 3, I'm going to take 3 to this power, 3 to this power. Okay. Remember the if and only if of our equality statements is if I have two things, I can take the same base to those two things and I still get an equality. All right, and then this 3 to the log base 3, that kind of cancels each other out. I'm just going to get n minus 10, and 3 to the first power is just 3. And then finally, add 10 to both sides. And there's your answer. Okay, what about this one here? I want to isolate the e to the negative x. So first of all, I'm going to subtract the 7 from both sides. I get -3 times e to the negative x equals -5. Dividing out the -3, okay, and I get -5 divided by -3, which my calculator says is 1.6 repeating. And now I have e to the negative x isolated, so I'm going to take the natural log of both sides. That cancels each other out, and I'm just going to get -x equals a natural log of that, which turns out to be that, according to my calculator. And then finally multiply by -1, and I get my final answer of this. All right. Okay, what about this one here? Gee, I know that 32 is a power of 2 to the 5th, and 4 is 2 to the 2nd. So I'm going to write it like this. 32 is 2 to the 5th. 1/4 is 2 to the -2. All right, to the x minus 3, and 2 is 2 to the 1st. So I'm going to write everything with the same base. I want to combine these all. So first of all, I'm going to do this by multiplying 2 to the -2 to the x minus 3 is 2 to the -2x over 3. All right, and then 2 to the 5th, and times 2. I'm going to add these. Okay, so I get 2 to the 5 minus 2x over 3 equals 2 to the 1st. Now I have the same bases, so I can equate the exponents. And then let's see here, what are we going to do? We're going to subtract 5 from each side. All right, I get -2x over 3 is equal to -4. I'm going to multiply each side by -3/2. So the negative signs cancel out, the 3's cancel out, the 2's cancel out. The only thing left on the left-hand side is x. And then over here, the negative signs cancel out. 4 times 3 is 12, divided by 2 is 6. So my final answer is x equals 6. All right, now let's do some problems. In 1994, a woman ordered coffee from McDonald's. It was too hot. She spilled it on her lap. It caused third-degree burns. She sued, and she was awarded $640K. This is a true story. Now, if the coffee was initially 180 degrees Fahrenheit, cooling coefficient is blah, which I looked up, or actually they gave us. The temperature of the room was 78 degrees Fahrenheit, and the safe temperature is 120. How long should McDonald's wait before delivering? Okay, so using Newton's law of cooling, all right, which is right here. Okay, we can solve this problem now. So let's see, we have to identify quantities here. T of t is the temperature after time t. That's going to be 120 degrees Fahrenheit after waiting for the coffee to cool a little bit. T sub s is the temperature of surrounding environment. That's the temperature of the room. T naught is the initial temperature. That's 180. K is the cooling coefficient, which is that. And T is what we're looking for. T is the time. All right, so plugging all this stuff into Newton's law of cooling, all right, we get this. 120 is equal to 78. I call this a copy step, so copy the data in. All right, then we have to solve this for t. First, I'm going to subtract those two to get that. Then I'm going to subtract 78 from both sides, and I get that. Then I'm going to divide by 102. Cancels out over there, and I get 42 divided by 102 is equal to that. Now I have e to the isolated, so now I can natural log both sides. According to my calculator, that becomes that, and then this is just negative 0.09 times t, and then dividing by negative 0.09 for each side, we get the time in minutes, because the cooling coefficient was in degrees per minute. Okay, 9.9 minutes. Okay, next. SpaceX's Falcon 9 has a takeoff weight of blah, okay, mostly fuel. After burning its fuel, its weight is that. If the exhaust velocity of the fuel is that, what is the velocity of the rocket? Okay, so the exhaust velocity of the fuel is 3,000. We're looking for the velocity of the rocket. This is the rocket equation, okay, where V is the velocity at fuel burnout, which is what we're looking for. W sub T is the takeoff weight, which was that. W sub B is the weight after burning its fuel, and C is the exhaust velocity of the rocket, which is 3,000. Okay, fortunately this is already solved for a variable, so we can just copy step right away. V is equal to that, all right. Pounds cancel itself out, as it must, and the natural log of 45,600 over 16,600, according to my calculator, was 1.0105, and so therefore the velocity of the rocket after burning its fuel is that. Okay, one more. In 1991, hikers in the Alps between Austria and Italy found a body laying halfway out of a glacier. They ended up calling him Iceman, or Ötzi, and carbon sampling was found at 52.5% of the carbon-14 he had at the time of his death. Okay, how old is Ötzi? This is the radioactive decay law for carbon-14. Okay. Dividing out to A0, we get this. A is the amount of carbon-14 he had in his body when tested. A0 is the amount he had when he died. This was 52.5%, or 0.525. All right, and then we have a function that we can end up solving for t, which we do by taking natural log of both sides. All right, according to my calculator, that turned out to be, oops, I guess I didn't do that yet. This cancels out to be that, all right, and then dividing that, and then you operate your calculator. Turns out that he's 5,200 years old. Okay. Okay.